Hydroboration oxidation. This is going to be an anti-Markovnikov hydration. So we're going to be adding a proton and a hydroxy. The hydroxy is going to be placed at the less substituted position. Okay, this gives us an opportunity that the acid catalyzed and the demercuration doesn't allow us. So the reagents here are going to be a boron trihydride, and it's going to be in tetrahydrofuran. It's a two-step reaction, and the second step is going to involve using peroxide and sodium hydroxide. So here's our pi bond. We have the less substituted position here. That's where we're going to add the hydroxy. So this will be our result. Now, in addition to anti-Markovnikov, I said that it was syn addition. And with syn addition, let me draw my substrate in here. That means that both the proton and the hydroxy are added to the same phase. And I will show you what I'm talking about. So if we have this reaction, we've got our less substituted position right here. That's where the hydroxy is going to go. And we're going to put our hydroxy on a wedge. That means that the proton also has to be on a wedge. The proton and the hydroxy will be, if one's up, the other will be up. We have, on the original molecule, we've got a methyl group here. It doesn't disappear, so it's going to be on a dash or away from us. The other possibility is that maybe it attract from the bottom, and so then we would have our hydroxy on a dash, and our hydrogen or proton would also be on a dash, and our methyl group that we started with would be on a wedge. So both of these forms would be made in the reaction. Okay. What's not made is where the hydroxy group is up and the proton is down. So we do not make proton down, hydroxy up. This is not made. And you also don't make the reverse. We don't make it where the proton is on the wedge and the hydroxy is on a dash. Okay? So that does not occur. So let's look at the reagents here. Boron is very similar to a carbocation. It lacks a charge, and but it also lacks an octet of electrons, so it makes it very reactive. It has an empty p orbital. And we have to keep it in the tetrahydrofuran to stabilize it. So let's look at some of the electronic considerations and the steric considerations that make this anti-Markovnikov. The pi electrons here are going to attack the empty B shell. I did not mean to make that green. We're going to make it orange. There we go. They attack the empty P shell. That makes this carbon here a little bit positive. And so these electrons here are going to be attracted to that electron because it's a little bit more positive than the other electron, the other carbon atom. So what we end up with is something that looks like we've got a boron sitting here. It's still got its 2 hydrogens on it. And our green hydrogen and its electrons are here. And that's put the hydrogen on the more substituted position and the boron on the less substituted position. Now, sterically, you can also look at this and say that the more substituted position is more sterically inhibited, and the proton here is much smaller than that large boron, and so it's easier for the hydrogen to get into the less substituted position. So let's consider the expected selectivity, regional selectivity, and then draw the product. Okay, so we're going to add, what we're adding here is a hydrogen and a hydroxy. We're not going to draw the hydrogen because we don't usually draw hydrogens, and we're going to add the hydroxy to the less substituted position. So this is the less substituted position, so we add the hydroxy here. Less substituted position, add the hydroxy there. Less substituted position, add the hydroxy there. Now, we've already mentioned that when we add these, we're going to add them syn. Both groups are going to be added to the same face. This is only going to matter if a chiral center is formed. If there's one chiral center, because we're working on 2 different carbons, if one chiral center is formed, we'll get both enantiomers. If 2 chiral centers are formed, we'll get 2 enantiomers, but we will not get the other 2. So I will show you what I'm talking about here. So here we have a reaction all set up for us. We have our double bond. We're going to add the hydroxy to this carbon right here and the hydrogen here. And we're going to make, at both places, we will have a chiral center. We have 4 different things attached. So we will make we'll add a hydrogen there and a hydroxy here. The compound already had a methyl group here, which will now be on a wedge, and it already had a hydrogen that we didn't draw and is now on a wedge. The other thing that could be formed would be, let's go back to our green, we could put the hydrogens on a wedge, and we would then put the hydroxy on a wedge. The methyl group that was at this position already will now be on a dash, and the hydrogen that was originally on this position will also be on a dash. What is not made is the molecule where hydrogen that we add is on a wedge and the hydroxy that we add is on a dash, or vice versa. So they'll both be on a wedge or both be on a dash. And you just have to be aware of what else is on here. You know that there's a hydrogen there, even though it's not drawn. Okay, so let's look at what happens when we do this on some examples. This is, again, a really good place to stop the video and practice before you go on. Okay, so we're going to add the hydroxy and hydrogen. We're going to add the hydroxy to this position right here, and the hydrogen will get added up here. And so if we add the hydroxy on a dash, then we'll need to add the hydrogen also on a dash, and that will push this methyl group that's already here to make it on a wedge. If we add the hydroxy on a wedge, then we'll also add the hydrogen on a wedge. Okay, so now we're going to add the hydroxy to here and the hydrogen to this to the ring position. Okay, so again, we're going to have to add, if we add the hydroxy on a dash, we're going to have to put the hydrogen on a dash. This is not a chiral center, though, so we won't make it a dash. Sorry about that. Not a chiral center, so we don't even need to put the hydrogen on there. The hydroxy could be on a dash. Okay. So the next one, we are going to add the hydroxy to the least substituted position. So we'll add it here. We have not made a chiral center. There are two hydrogens here, so that's not chiral. And there are two hydrogens here, so that's not chiral. So we don't need to draw any stereochemistry. We're going to add the hydroxy to the least substituted position, so we're going to add it right here. When we add the hydrogen to here, we will not make a chiral center, but we will make a chiral center when we add the hydroxy. So we'll put it on a wedge, and we'll put it on a dash. These two methyl groups are identical, so this is not chiral, but this is chiral. There's a hydrogen that we don't draw.